So we actually started with very compact boson stars. So these are almost neutron star density objects. But to be this compactness, the Hooke conjecture bound suggested that if you went to gamma of 11, we should form a black hole. So first let me just show you the low gamma case. So now we're starting them at rest. And so this is now just the mutual gravitational interaction. So those two lines represent the energy in the boson star. They collide. Now in this low gamma case, they actually do stick together. They form a large soliton that's radiating scalar energy. Now if you go to a moderate gamma, so you have a gamma of 2, now you see this, so what I mentioned, the fact that they don't necessarily stick together. So they're going to boost towards each other. There's going to be a strong perturbation because they are strongly self-gravitating, so this is not going to be clear window. But you'll see that in this case they actually just pass through each other and sort of explode outwards. Now going to gamma equals 4, now we actually do see, now gravity starts to win and we'll see a black hole will form. Just before I start, let me just explain. Actually, to get to these high gammas, we actually also have a change in gauge conditions in the simulation. And one artifact of that is as they get closer, so you can see that they're more Lorentz boosted. This is the direction of collision, so this is where it's being Lorentz contracted. As they get close to each other, they look like they're spreading. That's a purely coordinate artifact, they're not. But what's interesting about that is, at least you can sort of see this initial phases of this classical interference that starts. And so there they go. That's just coordinate. They start to interfere. But as they interact, and suddenly this horizon forms around them and sucks up most of the matter. And incidentally, that the horizon sort of shrunk afterwards is also coordinate. The actual proper area grew afterwards. Okay, so this is one example that shows, indeed at large enough boosts, when they interact, a horizon does form around them. So this doesn't sort of say necessarily why it's happening. And there's also something that's a little bit puzzling about that is, I mentioned that the Hooke conjecture argument said that this case is the critical case for the gamma of 11, and here at gamma of 4 already we found that. And you might say, okay, it's an order of magnitude, it's back with envelope calculation, what's the factor of a few? On the other hand, with this amount of energy, those two boson stars, they don't fit within this large radius, they're a factor of a few to large. So something else is happening here. So there's some other things going on. So you can imagine that if anything, the back of the envelope calculation, you might have had to go a factor of a few beyond, like gamma of 40 or something. So there's something interesting that's going on that's actually making it a factor of a few less. So what I think is going on, and I'll show some other simulations to sort of support this, and this is actually very consistent with some of the ideas that Penrose even came up with when he looked at these things from the point of view of just these colliding Eichelberg-Sexel solutions, is that it's really essentially, this is what's causing this is gravitational focusing. And perhaps even simpler than that, you can almost understand it as geodesic focusing. And so that's something that will explain, well, why it's a factor of a few less and why you can apply the Hooke conjecture to this in the first place. So imagine now we're taking out two solitons and now we're boosting them to very large gammas so that the curvature is being contracted to this, these very thin pancakes. So again, what boosting does, boosting doesn't change the curvature. So in the rest frame, they can have very low curvatures. And now in the high gamma limit, that curvature is compacted into these thin pancakes, and these act as gravitational lenses, basically. So essentially, this one boosted soliton is going to act as a gravitational lens on this one, and vice versa. And in the ultra-relativistic limit, because all of the influence has been compacted to such a small region, when these sort of two lenses interact, the particles from one that make up one soliton are going to be focused essentially instantaneously, so quickly that by causality, there's no pressure, no pressure can react to that to counteract the focusing. Perhaps this picture might show it a little bit more clearly. So to test that, we we wanted to go to higher gammas, and so I'll show you results from now fluid stars. This is the model soliton. The nice thing about a fluid star compared to a boson star, just for technical reasons, we could go to much larger gamma factors, meaning we could start with a much less compact star. So we were able to go to gammas of 10, and in this case, the Hooke conjecture would suggest, this is the compaction. The Hooke conjecture would suggest that a gamma of 40 would be the critical one above, which would form black holes. But first, let me just show you that just look at what happens just with this geodesic model. So what I'm showing you here is the example. So we're modeling this collision. So we've got these two stars that are boosted to each other with a gamma of 10. But in this picture, I've removed one of the stars. So the actual star that's producing this gravitational lens is coming from the right-hand side. They're going to hit at t equals 0. And the star on the left-hand side I've replaced with tracer geodesics. So now there's no dynamics, it's just a boosted solution. And what these lines are showing you are the geodesics from this other star that's moving over a gamma of 10. So you can see they're moving. Here they hit this lens and they focus down. And of course they're exploding, and this is just geodesics. So in some sense, this is sort of explaining, well, first of all, why it's happening at a factor of gamma, several less than what you predicted, because what's happening is that there's now a radial focusing. So this was the initial size of the object, but this lens is causing it now to focus radially. But actually, also, perhaps more crucially, and why I think now you can apply the Hooke conjecture, is what this lens has done is it's taken what has largely been kinetic energy and now converted it into a radial flow. And it's sort of at this stage where you can really apply the Hooke conjecture. So now sort of the lens has induced gravitational collapse. Now the Hooke conjecture can be applied. And so in some ways, this is why it's also generic.
And you get the icons.
Yes. So now, So I'll show you that. And this simulation is even more suggestive. What I'm going to first show you is the case where a black hole doesn't form. So this is now a gamma of 8 case. This is now, again, this is a fluid star. So this animation showing is the density of the star. So these are the two Lorentz compacted stars. And boost them towards each other with a gamma of 8. And you'll see that despite there being fluid stars, they're going to sort of essentially smash through each other, but now they're being focused down. And then at this point, so now they've been compressed down significantly, but the pressure in the stars builds up significantly, and here it explodes. And essentially, they weren't compressed to a radius small enough to form a black hole. Now we go to a gamma of 10, and so here a black hole forms. But what I'm saying, this is sort of suggestive of this picture of what's actually happening, is if you notice what's happening with the apparent horizons is we first find two separate apparent horizons, and then they merge to a larger one. So this is sort of at the threshold borderline case. If you could go to gammas of 20 or 30, you'd immediately presumably form a large apparent horizon. But the fact is that they essentially pass through each other. They start to focus, the pressure is not able to react, and so locally, this transverse flow has been converted into a radial flow. Okay, so, but we can go even further into this geodesic focusing, I think. So this is now getting more speculative, but it's based on sort of perturbative work by these people and some others that I'll show later, and also some numerical simulations that's at least consistent with this picture. So the way that I described them before is it's this geodesic focusing by the lens of the other object, and you sort of imagine the little particles following these geodesics. But I think that this picture is also explaining if you didn't have particles. If you sort of like, what is a curvature element, if you will, for lack of a better term, associated with one lens, how is that focused by the other? And so let's imagine, say, taking two black holes and boost them into very large boost factors. So all this could also be soliton particles. So this is where the matter is confined. And now we're not going to have a head-on collision. We're going to introduce some impact parameters. So again, these are boosted at very large velocities. This is sort of the Lorentz contracted curvature that's associated with each of these boosts. And they're going to essentially notice each other at when they reach this the origin here. And so just like before, where the little particle elements in the stars, they were impulsively focused, there was no pressure that could build up on such small timescales to make them resist this collapse. If you now think like what happens with local pieces of curvature, they're going to follow geodesics to leading order. And again, so essentially what's going to happen, so if you imagine here, so what I'm sort of drawing here is like how little bits of curvature elements are going to focus when it encounters a lens, say, and these bits of curvature encounter the lens, that's the particle. Now one thing with these boosted solutions is so the strength of the lens decreases the further you go away from the particle. So this is our lens. So the curvature elements from this particle that are closer to are going to be focused then by a larger angle than those that are further away. So essentially in this case what's happening is an initially planar front, when it encounters this lens, is going to get curved. It's going to be bent. But if you think of what happens at a sufficiently large distance afterwards, let's think of a large impact parameter, so a black hole doesn't form. So they just deflected the two little black holes and then moved afterwards. Well, at some point sufficiently far past the interaction, they're just going to be loaded as boosted black hole solutions as well. So the curvature that's associated with them is again going to be the plane transverse. But that can't be the bits that were bent by this initial interaction. And so if this geodesic focusing, what it's essentially doing here is converting these sort of bits of Coulomb curvature into gravitational radiation. And that's sort of, in mathematics, at least at the perturbative level, that's what these people did in this calculation. So at least at that level, that's sort of consistent with what they were doing. So another calculation that's also consistent with this was looking at this effective field theory work by Galley and Porter. And they again took this ultra-relativistic scattering problem, so a large impact parameter, and they found that the radiation was strongly forward beamed in this direction. Again, this is quite consistent with the picture that the reason why the radiation is being beamed is sort of curvature elements can convert to radiation, but it's in the direction of focusing. Now the one simulation result that to some extent gives a little bit of evidence for this. It's not quite clear-cut for several reasons, but let me explain this. So this was work with Uli Spurok and collaborators. And we looked at now the grazing collision of two black holes. The two caveats. One is that we didn't go to very high gamma. So this is actually a very modest boost, gamma of 1. So it's still very much the RSMAS-dominated regime. But let me sort of explain what's happening. So we have two black holes. Here, one black hole is moving in the negative x direction. So the center of mass is at 0. There's another black hole that's moving in this direction. We just didn't draw it here, not to cover up the figure. So we only showed one black hole. And what we did is we tuned the impact parameter. We wanted to get to a situation where we could get as much radiation produced. So the Herald collision produces a fair amount, but the most radiation is produced sort of at the threshold. You get sort of zoom wall orbital dynamics. And this is a regime that's close to that. And what this figure is showing here is a circle is sort of a measurement of the size of the black hole. So we measure the irreducible mass, and then the radius of the circle here is a representation of that. So the surprising thing was, at least when we first saw this, we couldn't understand what was going on. So we had these black holes that essentially one little loop. But notice how big this black hole is compared to the initial condition. And this is sort of showing what's happening to the irreducible mass at this interaction. It's almost growing by 50%, which is it's very difficult to understand in the sense that, okay, now we've got the zoom wall motion, it's producing radiation. At least we naively thought it was going to be isotropic, or most isotropic or quadrupolar, so more like the astrophysical orbital case. But if you think even with the black hole that's this size, if it is emitting so much radiation isotropically, the cross-section is just not large enough for this black hole to absorb this much energy. It didn't seem to expect it to be radiated. And so in some sense, the only reason that, or one reason which explains this is now going back to this focusing picture that I mentioned, is if you imagine that these are essentially almost lenses now that are focusing the curvature. What's happening is when they first collide, they produce a tremendous amount of gravitational waves, but it isn't being emitted isotropically. it's being beamed in the direction of motion, but it's also being focused downward. And so it's being focused towards each of the black holes. And so that's why they're absorbing the energy. So I mentioned like the one caveat, this is low gamma. The other caveat is that we can't measure in any invariant sense gravitational waves in this strong field regime. What we usually do is go far enough away that we can use to the asymptotic fat analogs of what I was talking about to measure gravitational radiation. But in this highly dynamical strong field regime, there's no unambiguous notion of gravitational energy that I know of. So we can't really measure to see if that's actually what's happening, but it's at least consistent with this picture. And if this really is the case, that this an interesting, at least thought experiment consequence of this, well now let's imagine we did go with very large gammas. Let's say pick a gamma, pick your favorite large number, a million or a billion. So now the black holes, the rest masses, they'll become very small, essentially point particles. Now again, if we increase the impact parameters so that we have this threshold, you can imagine that there's going to be a regime where we take these two infinitesimal microscopic black holes, we scatter them off each other, and what emerges are two macroscopic black holes. A million, a billion, whatever number you want times larger than before. So I'm not sure if that's what will happen, but I think that's a very interesting consequence about if this focusing is what's described in what's going on here. Okay, so in the last few minutes, I just want to finish up with some open questions. And I've raised a few questions just within this discussion of this ultra-relativistic limit, but I wanted to make some connection to some other areas of strong field physics in the last couple of slides. So one question, as I mentioned before, sometimes the first one of these calculations is what Penrose when he took the infinite boost limit. But that is a pretty bizarre limit in the sense that once you take that limit, there's no notion of rest frame. What this gravitational shock wave, you can't go back to this rest frame. So it seems as if the finite but large and infinite boost limit cases are the same limit, but it's because they are so different, it would be interesting to see if that's really the case. And it's still an unsolved problem. What happens to the causal future of the collision of two Eichenberg's excel solutions that Penrose studied back in the 70s? Another interesting question, and I think I'll just take a few minutes to talk a bit more about critical phenomena. So this is a conference where we're celebrating 100 years of GR, all the interesting things that happened, the interesting things that we can think about. And unfortunately, there's no talk here on critical phenomena, which I think is that Matt Chopwick discovered about 20 years ago, which at least in the recent history of the field is one of the most, in my opinion, one of the most fascinating discoveries of properties of relativity. So just in a nutshell, what critical phenomena is, so we have looked at gravitational collapse at the threshold of black hole formation. So that's if you take some distribution of matter or energy, even nuclear gravitational waves. If you don't have very much, then, for example, with the scalar field is what you originally looked at, and you look at the evolution, it's just going to disperse, it's like radiation. If you take a very large amount of energy, the self-gravity is going to make it collapse to form a black hole. And so stimulated by questions by Tristan Dulu on what happens at the threshold, essentially he wanted to ask, what is the smallest mass black hole that you could perhaps form in this system? He tried to study the threshold of black hole formation. And he found this quite surprisingly remarkable universal behavior that emerges, essentially that the solution approaches a universal, discretely self-similar solution with these universal scaling and echoing exponents. So universal in the sense that it doesn't seem to matter to depend on the initial conditions. These numbers pop out of a solution or out of a system which has no intrinsic scale. So it's a very interesting behavior at the threshold of black hole formation. So one question I'm getting, applying this to the collision problem, what is the nature of the threshold for the collision problem? It's actually, it seems like there actually might be several thresholds that are relevant. At a first glance, it seems that, again, because there's conjecture that matter doesn't matter, it's really a gravitational effect, it should be the gravitational threshold solution, the one discovered by Evans soon after Matt did his work with the critical
scalar field solution. On the other hand, what the Abrams-Maven solution is also a self-similar solution. So what the dynamics is doing is, with a self-similar solution, you're revealing smaller and smaller scales in the problem as you choose those from close to the threshold. So at some point with one of these collisions, you'll eventually get down to the small scales that describe the source, whether it's a black hole, a boson star, a fluid source, the Eichelberg-Sexton solution, that's a singular source. So at some point, it might be that the ultimate threshold solution is governed by the source of this near-pancake solution. On the other hand, as I sort of described before, with what the two black hole case suggests is that there might actually be sort of three generic outcomes in this case. That if you now include impact parameter, at very large impact parameter, there's just going to be a deflection. So let's imagine two solitons as the sources. So there are no black holes. So that the one state is no black holes, they deflect, there are no black holes in the final state. If you look at the Heron collision case, it's going to be a single black hole that forms. And now with one of these grazing cases where there's a tremendous amount of focusing energy, you might form two black holes. So this would be a situation where there's 0, 1, or 2 black holes as the outcome. There could be very interesting behavior at the respective thresholds. Another interesting question is, what is the relation with, now if we look at the, perhaps either the finite boost or the infinite boost Eichelberg-Sexton solutions, and the infinite plane front gravitational wave shockwave solutions that again Penrose initiated study of in the early 70s. So as I mentioned, with the Eichelberg-Sexton solutions, there's really a curvature singularity at the origin. That's what the limit, that's where the black hole horizon was. But the curvature, it's a plane-fronted wave, but the curvature also as you move away from the center. But Penrose looked, another thing that Penrose looked at in the 70s, and Penrose and Kahn, were now if you take these plane-fronted shock waves, but you impose planar symmetry. So these solutions actually don't have singularities, they have planar symmetry. But what they found is that generically, it doesn't matter how small the curvature is, after they collide, they form naked singularities. Now that's not considered a generic counterexample of cosmic censorship because the planar symmetry is so asymptotically flat, but actually perhaps even more so because these solutions are somewhat pathological. And actually, if you sort of apply this focusing arguments that I suggest, that even though the curvature is arbitrarily weak, these infinite plane-fronted waves are in some sense infinitely strong in their focusing power. They essentially focus all of space down to a point. And the question is now, if we say we don't have except the point particle Eichelberg-Sexton, we have the infinite plane cases, well, we look at a scenario where it's got almost planar symmetry in a certain regime that then becomes some finite extent regime that looks like a plane for a while. And to lie these two, what's going to happen? Will you get a naked singularity? Or because of the fact that it's not an infinite plane anymore, perhaps you won't get any singularities, and perhaps a black hole would arise. One reason why you think that there will still be at least naked singularities locally is you can make in some sense, what Penrose and Kahn show is that the stronger you make the curvatures, the sooner after the collision you get naked singularities. So if you have a sufficiently strong planar region, you can at least make that planar region, the extent sufficiently large that by causalities, edge effects won't be able to prevent singularity from forming in the collision. And then you might say, well, okay, so we get a singularity, but perhaps eventually a big black hole will form and encompass this region. On the other hand, this is your speculation. For one's now said perhaps there's a place in the universe where these near infinite plane waves are relevant, and those are in cosmic bubble collisions. So in these scenarios, the universe is in a false vacuum state. There's bubble nucleation that creates a bubble of true vacuum and a false vacuum. And these bubbles start to expand outwards, they accelerate, they eventually approach the speed of light. And at least at first glance, seemingly paradoxically, as they expand, they gain energy. But that's because inside is a true vacuum that's a lower energy state than the exterior. So in some sense, they're scooping up all the energy of the false vacuum. And so very quickly, they asymptote to relativistic
almost plane-fronted shock waves. And so you have two of these bubbles that form when they collide. If they're large enough when they collide, they're going to be almost planar in some region where they collide. Of course, there's going to be some curvature, and that will set the scale. But in some region, they're going to be almost planar. And there's been suggestions that there could have been bubble collisions in our past, and that might imprint itself in the cosmic microwave background. But then the question is quite relevant. If these things are in some sense close approximations to these general quantum solutions, that might be a very bad situation if they can singularities over the form. And so, and if, for example, if we're in that region, it's not going to help us if someone says, well, don't worry, cosmic censorship's fine, because they're big black holes eventually going to consume. Right? If there was a cosmic bubble collision in our past, now there's a big black hole horizon around us, that's not necessarily a comforting thought. So I think there's some, still in the social intimacy, there's some interesting questions. Now, what happens when you have these near-planar bubbles? And there are a couple of things that you can imagine could happen. Is one, well, they're not exactly planar anymore. And particularly in something like the universe, as they expand, they're encountering homogeneities. And that's going, and if they're not exactly planar, if they're like ripple with ancient homogeneities, that's going to weaken the focusing effect. And so you can imagine that might be enough that it prevents naked singularities from forming. On the other hand, it might be that these things are highly unstable. I was just pointing out there's some very interesting work by Grady collaborators the last couple of years that looked at these domain wall collisions, actually without even including self-gravity, and they find that they are very unstable. So it might be that this picture that these bubbles can expand indefinitely is very wrong. That at some point that they become very unstable, and there's some much more interesting dynamics that happens. Okay, so I'll now add some other slides about stuff, but let me just go to the conclusion. And then let me conclude sort of by going back to my personal reflections of the last 100 years of this dynamical strong field regime, and just say that what I think the future is going to be. And in some sense, I was a bit pessimistic, saying the inverse dark ages, we were perhaps, all of us, we've been too excited about black holes and gravitational waves in the cosmos, and sort of taking these solutions for granted. So I was kind of critical on that. Perhaps that sort of thought process, but in some sense the reason why I'm being that critical is I think we're really at the core of a new era in gravitational science where, in particular, gravitational wave detections, LIGO, possibly pulsar timing, hopefully space-based detectors within the next few years, we're really going to directly probe this dynamic strong field. When two black holes collide, the gravitational waves that they emit, the structure of those waves is as directly sort of probing that regime and seeing it as we possibly can. Likewise, the imaging of the black hole is shadowed by the Event Horizon Telescope. They're already probing scales that are close to the horizon radius, and they expect within a few years to actually see the shadows of the black hole. So I think it's not a situation where we become too complacent in taking these solutions for granted, because there's going to be evidence, I think, one way or the other, about this very interesting regime of relativity. The part of it that I spoke about, focused on more today, is the relativistic regime. Again, I'm not sure how connected it is to the astrophysical strong field regime. There might be some interesting connections. But anyways, I think the next few years is going to be very exciting. Thank you.
For this very interesting talk. Are there comments or questions?
Can you tell me, have Bose's stars been seen? Have they been observed?
No, not. So, yeah, the simple answer is no. The slightly more, I believe, so Andrea guesses to the gas station said that fermion stars were ruled out as possibilities for the central supermassive black hole. I think if you tweak parameters of the theory, you could still make it at least plausible that some of the dark compact
I'm
objects...
sorry, I understand very badly. Can you just say yes or no? Have they been seen or not?
No, they haven't been seen if you assume that the dark compact objects are actually black holes.
in principle, they could be boson stars. So it's no if you believe that the dark compact objects are black holes.
I'm intrigued by this last bullet point. I've never thought about taking two small particles, two objects, making them ultra-relativistic and then colliding them, because obviously the properties probably don't depend at all on what the objects are. It's all just kinetic energy. So there's two questions. One is, probably I would guess that the waveforms that come out of such collisions are rather universal, which means they only depend upon maybe length scale and angle. Is that likely to be the case? Because if so, it would be nice to know what those waveforms are so that we can look for them. And then the second question I wanted to ask is, thinking about that, of course, in the rest frame of either particle, it's just a happy particle running along, I mean, doing nothing. What does this collision look like, not in the center of mass frame, but from the rest frame of one of the other particles? Because it's a bit strange to see how the black hole forms in that case.
Yeah.
So, two questions.
Yeah, very good question. So with the first one, so the waveforms, if this universality conjecture is correct, it will depend on the impact parameter, but for a given impact parameter, it will be the same universal one. For instance, with the head-on collisions, yes, so the head-on collisions have been at least a finite boost, using black holes as a model particle. And it's a very simple structure. It's really like one big pulse followed by a ring down. When you start increasing the impact parameters, there's some orbital dynamics. It looks like there are a few additional cycles that are associated with orbital motion. But then it's again, when it finally emerges, it's a weakness associated with this final black hole.
If the hoop conjecture is well satisfied, there is no orbital conjecture, which I think is important.
So if you start with impact parameters that are larger than what the hoop conjecture, so at some point, the hoop conjecture says they won't form a single black hole, but then they will actually be orbital dynamics.
I think the first case is more interesting. Yeah. Okay, the second question, what does it look like in the rest of it?
Right, so that's bizarre. If you think about it, in some sense, so for example, let's say we have very small black holes, a very large boost, we go to the registry of one. What it can seem like is this sort of iconoclastic shock wave is approaching it. The same thing, right? So you've got 4 electrons sitting here, no horizon. There's this huge iconoclastic shock wave coming towards it. It's going to hit it, but it's going to sort of drag it along. And in some sense, it's going to look like it's going to get stuck in that solution, and eventually a black hole is going to form and it's going to grow. And eventually you'll have a black hole that's almost most of the mass of the space-time, but it's receding at relativistic speeds. So in some sense, it's saying that these iconoclastic solutions are wildly unstable. They're electrons.
I'm more bothered by just the case of 2 electrons, which is each.
Yeah, so
the rest frame looks perfectly normal.
So the gallium electron in the rest of the one looks like it's the cyclohexagon solution that's approaching it. So it's, from its perspective, it's got a huge energy. And yet, when you snag it, drag it along, and eventually this thing's going to grow into a huge black hole solution that way.
I have a similar question. That's a beautiful picture you have there. Are there generic things you can say if these black holes are spinning? I mean, you already have these very interesting things right there, focus with each other, which I would have imagined. But now if they're spinning, are there things that look much more like 2 magnets? What happens? There's spin interactions, spin orbit terms that, you must see these things in your simulation.
Yeah, that's a good question, but this also goes to the point that the matter is irrelevant. So spin becomes one of the properties of this matter that's sourcing it that becomes irrelevant. So the larger the boosts are, it just becomes closer and closer to this hyperluxation collision. So the spin becomes irrelevant in a large boost limit as well.
Can one imagine the quark entrapment in collisions, very high energy forming nucleons as black holes?
I'm not sure if I understand the question, but at least it's an interesting thing like with the LHC. Let's suppose there was a Planck scale. It was Planck scale. Actually, what I'm talking about here is when you quite a bit above the Planck energy. So interesting, as you approach this Planck energy,
you're going to go through the regime where quantum gravity is essential to understand what happens before you get to this next classical gravity regime. And yeah, there, the quark confinement as it breaks down as you approach the quantum regime, or whatever is happening will be very relevant to describe it. If you go sufficiently above this energy, in some sense, what this conjecture is saying is it doesn't matter. It doesn't matter if they confine or if they not. The horizon is going to form around and sort of screen all the interesting things that might be happening.